think last year I used one of these for a while.
So the counting numbers, 1, 2, 3, 4, 5, 6, mathematicians call those the natural numbers. And then we get this new fancy symbol for the natural numbers. It's like the letter N, but it has an extra little line in it. It's kind of cool. So those are the first numbers that existed. People started counting with their fingers. Okay? Then a big breakthrough in mathematics. I don't know if it was a breakthrough. Someone lost all their fingers. And they're like, how do we say that? How does that person count anymore? They have 0 fingers. So the whole numbers is the same as the natural numbers, just one thing is added. So they add the 0. So you've got your natural numbers. And your natural numbers, you think of it, some people think of this like a bucket of numbers. Then the whole numbers is another bucket, but that bucket only has the 0, and you put the other bucket inside. So it has all the natural numbers plus 0. Then somebody moved to Canada, and the temperatures got really cold, so they had to include negative numbers. And if you have the positive natural numbers, 0 is a whole number, and now you include all of the negative numbers, you get the integers. The symbol for the integers is either an I with a double line or a Z with a double line. They use the Z more often in higher level math. It actually comes from the German word for number, Zahlen, which starts with a Z. Which means if you had the number 2 and someone said, what number of families does the number 2 belong to? You would say, it belongs to the natural numbers, and it belongs to the whole numbers, and it belongs to the integers. Then we have what are called the rational numbers, which is every number that can be expressed as a fraction. This includes every decimal that ends, terminates, or repeats. Because if you have a decimal that ends, you learned in your last unit, you could change it to a fraction. So anything that you could write as a fraction is called a rational number. And they use the symbol Q for quotient. Quotient means dividing. And any fraction basically means something divided by something else. Okay? And every decimal that repeats itself can be written as a fraction. Does anybody know what 0.3 repeated? Which fraction that is? If you go to your calculator, like 1 over 2 is 0.5, right? Have you ever seen 0.3 repeated on your calculator? It's 1 over 3. If you try it on your calculator right now, you do 1 divided by 3. A whole bunch of 3's show up.
Oh, I was going to say, why was I thinking 3 over 9?
3, and it is also 3 over 9. In fact, any single decimal repeated, you can always make over 9. So 0.4 repeated, oops, is 4 over 9. This. And anything that repeats itself with 2 numbers, you can write as a fraction as 23 over 99. And anything that repeats itself over 3 numbers, like 0.571 repeated, would be 571 over 999. So everything that's a fraction is called a rational number. But there are some numbers that cannot be written as fractions, and those are called irrational numbers. It includes a lot of square roots, like the square root of 2, the square root of 3. Does anybody know why it does not include, I'm going to put an X through it, the square root of 4? is the square root of 4? What times what is 4? 2. So the square root of 4 is not an irrational number because it's equal to 2. And 2 is a fraction, 2 over 1. It's a rational number. It's also a whole number. It's also a natural number. And then there's special numbers. There's special numbers like pi. Have you heard about pi in circles and stuff in middle school? It's approximately 3.14, but if you did all of the decimal places, it goes on forever. In fact, there's sometimes competitions to see how many decimals of pi you can remember.
Does it like ever stop at something?
It never stops. It goes on forever without a pattern. In fact, every irrational numbers, it says decimals that do not terminate or repeat. They're all decimals that go on forever and ever and ever and ever. So like you can, if you want to, you can probably find on the internet someone selling a poster of 1 million digits of pi. It would just be a poster with just 1 million numbers on it. I don't know what you would do with that. Put it up on your wall and be like, oh, cool. I forget what the record of someone who did over 100 digits of pi last year in a competition at the school, memorizing. I even have a little book over here, all about pi. And in this book it says there is, here we go, let's see where I can find it. Yes, there are some people who like to memorize digits of pi. That's their hobby. And this one guy, his name is Hideaki Tomoyori. He recently did over 40,000 digits of pi from memory. That's 40,000 random numbers in a row without screwing it up. That's pretty amazing. It's also kind of scary. Like, what do you do with your free time? Do you know how long it took him to say that? Like, I've got like 3.14 and there's like 1.5. I've got like a couple more digits than just the 2, but not too many more than that. It took him 17 hours to say them all in a row. I don't know what's crazier, Mr. Shirk. 17 hours saying them all in a row, or if you're the guy that's listening for 17 hours going, Can you imagine you're in 5 hours, you're like, oh, sorry, what was that?
Yeah.
That is a lot of things. So what's going to happen is I'm going to give you a number. Like, I'm going to give you 2. And you would have to say that 2 is a real number because that's all numbers. It can be written as a fraction, so it's a rational number. It is also an integer, a whole number, and a natural number. So the number 2 belongs to 5 families. Whichever number I give you, you'll have to say which families it belongs to. So there's a way that we remember this, and that is with this picture. There are 2 main circles in this picture. If you have a highlighter, or 2 different colors, if you have a red pen and a blue pen, there's this circle in yellow and this circle in green. The green circle is the irrational numbers. The irrational numbers, those are the numbers like pi or square roots that continue forever and never repeat. The yellow circle are every number that can be written as a fraction. And in the yellow circle, there are some numbers that are only fractions. There are some numbers that are positive and negative whole numbers. There are some numbers that are just positive whole numbers, including 0. And then there's the natural numbers. So, in the yellow circle, there is, I'm going to run out of colors here. In the yellow circle, there is the orange circles inside of it, and then there's a green circle inside of that one, and this purple circle inside of that one. And so if something's in the purple circle, it's also in the green circle, it's also in the orange circle, it's also in the yellow circle.
And outside.
And everything is in the blue box, which is all real numbers. So if I give you a number, it's for sure in the blue box. You have to find out which one is it in the smallest. So if I gave you the number 5, here I'll do it in purple. You see 5 is a counting number. It's in the natural numbers. And since it's in the natural numbers, it's also in the green, also in the orange, also in the yellow. So 5, the smallest one is the natural numbers. But it also includes the whole numbers, the integers, the rational numbers, and of course, it's a number, so it belongs to all the numbers.
Do you have to write the double lines?
It's how they write number families. Like on the thing, it's bolded, but it's hard to write bolded. You don't have to, but that's generally what it's written as. If I picked 0, 0 isn't in the purple one. The purple one just starts with 1, 2, 3, 4. 0's first one would be the whole numbers. Then it's also in the I, it's also in the Q, and it's also in the R. It's all the numbers after that. So 0's in the green one, but not in the purple one. An integer, the orange one. If I pick something that's just in the orange bucket, that would be like -7. -7 isn't a whole number. It's not a counting number. Never met someone with -7 fingers. Okay? It is, the first one that is an integer. If it's an integer, it's also in the yellow, and it's obviously a real number. If I want to pick something that's just in the yellow one, ooh, this is going to be hard to see, but I'll use the yellow pen. Yeah, if I get mad at you guys, then I'm going to just take notes in yellow pen and make your eyes sore. If you have a fraction, isn't that hard to see? Not too bad. Whew. If you have a fraction like 2/3, it's not a counting number, not 1, 2, 3, 4, it's a fraction. Any fraction that isn't a whole number, those ones would just be fractions and real numbers. And then in the green, fluorescent green one, here we go. If I had the square root of 7, that is an irrational number, which is Q with a bar over top, but it's also, every number is always a real number. So when you're given a number, one of the things that some people do is they first decide which of the two main ones is it in. Is it in the yellow big circle with all the families, or is it an irrational one on its own? Once you've decided which one it's in, you find the smallest circle that it belongs to. And once you have that small circle, it includes everything bigger than that that fits into there. So we're going to do some examples. And first of all, we're just going to see if we can figure out whether these are fractions or things that aren't fractions. Irrational or rational numbers. In other words, is it in the yellow circle or is it in the green circle? The highlighted yellow or the highlighted green? In order for something to be a rational number, these are all things that are possible fraction. Is 3 over 4 a fraction? Yes. So that one, whew, not what I wanted. Where did I put my hair? That one is a rational number. We're just trying to decide if they're rational or irrational. If you type square root of 2 into your calculator, we're stealing stuff to see if we make it. If you go to your calculator, I'm going to show you sometimes you can figure out square roots with your calculator. So what I'm going to do is I'm going to open up my calculator here. Oh, I even have it in there already, but I'm going to do it again. Second, if you're unsure if a square root is irrational or rational, you can type them into your calculator. If you push enter and it's a long decimal, it's going to be irrational. If I did, here I'm going to do a square root. I'm going to pick one that I think most of you might not know in mental math. Anybody know what the square root of 121 is? But when I push enter, it's perfectly 11. So this square root, because it's a nice number that ends, is a rational number. But a square root that has decimals with no pattern that keeps on going is an irrational number. We go back to our notes here. Square root of 2 would be irrational. Can you write 5.456 as a fraction? Or does it continue on forever? As a fraction? What number would I put on the bottom when I go to 3 decimal places? 1,000. And since I can write it as a fraction, it's a rational number. You just have to know that pi is an irrational number that goes on forever. 4/9, that's already a fraction. I can put fraction or rational number there. Square root of 4, so then if I'm unsure, I go to my calculator. What is the square root of 4? It's 2. Can you write 2 as a fraction? You can write it as 2 over 1. So because it's a nice number, it's rational. Now with a decimal, if the decimal has dot, 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 this means that it keeps on going. If it repeats itself, do you see any pattern in those numbers? No, I agree. So if it does not repeat itself and goes on forever, we say that's irrational. H though, do you see that H? 1, 3, 1, 3, 1, 3, 1, 3, 1, 3 keeps going. So we could draw that with a 1, 3, the bar over top of it, saying that that pattern repeats itself. And any repeating decimal is a fraction. In fact, this would equal -1 and 13/99 if you wanted to write it as a fraction. All right. So next one. This was just the 2 main families. If you had to list all the families, I would first decide rational or irrational. You're always going to have a real number. And then you decide which ones it all fits into. So, next question. Decide which families it all belongs to. First of all, these are all numbers So we can put R for all of them. They're all real numbers. That part's easy. They're all going to be real numbers. Next, decide if it's going to be a fraction or not a fraction. And I'm going to, on the page here, I'm going to take black circle for that one, green circle. Okay, they're all real numbers. Real numbers are split up into two groups, rational and irrational. These are the ones that can be fractions. These are the ones that can't. Okay? In the rational one, you've got your integers. I went green again. Your whole numbers, and then blue, your natural numbers. The pictures like this can be helpful. So, when I get to 44, is it in the rational? Is it a fraction or not a fraction? Can you write 44 as a fraction? 44 over 1, yes. So then this one will also have the cube. Then in the cube, what's the smallest one it belongs to? Is 44 a counting number? 1, 2, 3, 4. Would you eventually hit 44 if you kept counting? Yes. So it belongs in the blue, which means that it's also in the red, in the whole numbers, and in the natural numbers. So if you're in the smallest one, you have all of the other ones that are in there. -3. Can you write it as a fraction or not? Can I put it over 1? -3 over 1, is that a fraction? Yes. So because it's a fraction, we have this one. Then we look in the fraction black circle. If you're counting 1, 2, 3, 4, 5, 6, 7, the natural numbers, would you ever hit -3 if you're counting 1, 2, 3? No. What happens, the whole numbers, I include 0. So if I start at 0, 0, 1, 2, 3, would I ever get to -3? No. So that it is an integer, but it's not a whole number, not a natural. Whew. Is 0 a fraction? Can you write 0 over 1? Is that allowed?
This one's tricky. I
This
can't
one's tricky.
remember.
You can write 0 over 1. Look at, if I go to my
Which
calculator.
one's undefined and which one's...
Yeah, if you have 0 on the bottom of a fraction, that's bad. But if I go to my calculator and I type a fraction, and I put 0 on top and 1 on the bottom, that's equal to 0. So you can write 0 as a fraction. Which means that 0 is a fraction. It's also the smallest one in the fraction one. It's not a natural number because natural numbers are 1, 2, 3. But it is a whole number, so we would have whole number. And because we have whole numbers, that's inside of integers, we'd also have integers. 5/9, that's a fraction. But it's not whole numbers anymore, positive or negative, so it doesn't have integers, doesn't have any of these other three. Okay, we've got a decimal. It's continuing forever, so it's a possibility of irrational number. Is there a pattern? No. So this one is our irrational one. Nice thing about irrational, it's in this circle all by itself. Nothing else you can do there. -2.3, that is -2 3/10. So it's a fraction. But it's not a whole number, so it's not going to be the integers, whole numbers, natural numbers. So this is our challenge. Which families do things belong to? Now I'm going to do page 4, a little bit of page 4, and then I've got some stuff to work on. So these Page 4 is just other interesting things. Have you ever heard of prime numbers in math? A prime number is a number that is only divisible by itself and 1. Why is 6 not a prime number? Anybody tell me?
Because you can divide it by 2.
You can divide 6 by 2. 6 is 2 times 3, so that makes it not a prime number. Okay, I'm going to try to pick. You notice that after 2, 2 is the only even prime number. All the other ones are odd. I'm going to pick one bigger than 17. What about 27? Is 27 a prime number? Or is there something else that times, is it only 27 times 1? Think of your times table. Or is there anything else that times you can get 27 with? 3? 3 times what? 3 times 9, yes. So 27 is not a prime number.
I have a brain fart.
All right? In fact, like, this is crazy. There used to be online, I can even show it to you. They put very big numbers online. And they said the big number that we put online isn't a prime number. Like if I put 27 online, I would say 27 is not a very big number. Okay? But the question was, here's a big number. Can you tell me 2 numbers that multiply to this big number? So if I give you 27, right? Who said 3 times 9 first? Okay, so I would give Noel $10 for getting the first answer. That would be pretty sweet, eh? Okay? But it's hard. Do you want a challenge? You can. I even let you use your calculator. I'll give you a challenge. I'll give you 1 minute. If anybody gets it in 1 minute, even with your calculator.
Should I need a calculator?
Oh, maybe, I don't know. Let's see if you can figure this one out. The answer to the 2 numbers that I've multiplied together is 1,599. What 2 numbers multiply to 1,000? Oh no, just wait. I'm going to give you a different one. Not 1,599. I'm going to give you. Sorry, I'm going to give you 3,599. I need you to tell me 2 numbers that give me 3,599. You only have a minute. I'm going to set a timer. I'll give it candy. I don't have any candies here, but if someone figures it out in a minute, well, I'm giving you more than a minute, so it's taking me that long to get my timer started. There we go. 2 numbers, and the answer is 3,599. Good luck. You can use your calculator. No. So something, this is what you're at, this is what I'm giving you. Something times something. I hope I picked something that works. Or maybe 3,599 is a prime number, and there is nothing. That would be super mean of me, wouldn't it? And then you try all that work for nothing.
Voy a poner de esto acá.
No, it's different. These are just prime numbers. As 2 is 1 times 2. 3 is 1 times 2. We don't include 4 because 4 is also 2 times 2. Oh, that minute was fast. Nobody got it.
No, I think I know.
Okay. Check it out. I don't know. Maybe I was off. 59 times 61. Yeah, 3,599.
That was legit my answer.
That was just got it. Just 2 seconds after the 1 minute. Okay. That's super hard to find, right? I'm going to show you Okay? Here we go. I'm going to just show you this. I'll pull this website over. They actually did this online. They had a factoring challenge. It was wide open. And not only did they open it up, but they also gave prizes. The first prize, whoever got it first got $1,000. And just like I gave you 3,599,
There.
they had bigger numbers than that. You want to see how big the $1,000 prize was? You ready for the number? They're allowed to use. That's the number. Look how big that is.
9.
And you had to find two things that multiplied to give you it. And the first person to find the two numbers won $1,000. You know what's crazy?
Do they just have to look at the last X amount of numbers to figure it out?
What's crazy? Look at these ones. Still unsolved. Still unsolved. 100 grand for this one. 150 grand if you get this one.
Aren't you trying it, Jared?
Still unsolved. 200 grand if you get this one. You want to see how big this number is? There are two numbers that multiply to get that number. If you find out what those two numbers are, $200,000 prize. That's because in mathematics, like when I gave you 3,599, it's actually hard to find two numbers. It's really easy for calculators to multiply things, but it is not easy for us to find out what two things. And usually they're two very big prime numbers to make it work. Okay, that's interesting. Prime numbers. Perfect numbers. We call a number perfect if you add up all of the things that you can divide. So 6, you can divide by 1, you can divide by 2, you can divide by 3, and you can also divide it by 6. If you add up whatever you can divide it by, except for itself, and it adds up to the number that you had, it's called a perfect number. There are only 4 perfect numbers less than 10,000. 6, 28, 496, 8,128. Finding the next perfect number would be very, very hard. And these are just kind of fun. Have you ever heard of a palindrome before? Yes? You have palindromes in English and you have palindromes in numbers. If writing it forwards and backwards is the same thing, it's a palindrome. For example, in English, race car. What if I spell it backwards? R-A-C-E-C-A. It spells race car backwards too. That's kind of cool. Some people's names are palindromes. Like if your name was Hannah, H-A-N-N-A-H.
I knew a Hannah whose name was spelled that way.
Yeah. And then if it's spelled that way, it's spelled forward and backwards. I'm sorry, I spelled my name backwards. What's your name? It's actually Anna, but I spelled it backwards for you. So we have palindromes in English. And there are people who write whole sentences, who try to write whole sentences that if you write them backwards, it's a palindrome. What is Panama famous for? You know the country Panama?
The Panama Canal.
The Panama Canal. Check it out. Whew. See if I... No, I can't remember how I... Because see, I got Panama here. And then, I thought it was a plan. Oh, yes. There we go. A man, a plan, a canal, Panama. If we start writing it backwards, a man, a plan, a canal, Panama. It's the same sentence forwards and backwards. And it also makes sense, which is kind of weird. Because you can write things backwards and forwards and then maybe it doesn't make any sense. But race car makes sense. But it's not a full sentence. That is a full sentence that you can write forward and backwards. Okay, so I have a sheet for you to do. This is where we're going to end in our notes today and end our video.